Okay, well, another thing that's very unique to large turbine engine aircraft systems is fire detection and fire suppression systems. Now, it's not saying that the recip world can't have that, or even smaller engines or smaller turbine engines can't have that. It's just they generally don't for simple weight, space, and cost really kind of curtails that. But whenever you have like a multi-million-dollar large turbofan engine that's going to be carrying hundreds of people, it makes sense to eat the cost. You have the space, and you definitely can take care of the weight side of it. So your LEAP engines, your big G turbofans, and that kind of thing, they all have engine detection or fire detection systems and fire suppression systems. So let's get started talking about that. Okay, so to get us started, we're just going to talk about the different types of fires that you could potentially have and the different fire zones that we use in aviation to make decisions and to communicate where the fire is at effectively.
Okay, so now we've seen this before. There's the different types of fires that are out there. So Class A fires are your ordinary combustibles. It's what most fires you see. You see it, big forest fires on the news. That's a Class A type fire. It's all paper and cloth and plastic and wood and so on and so forth. You will have some of that on aircraft, some of that in a power plant because there's things that could potentially burn, even though a lot of that has been either at least taken out altogether, or if it's not taken out, it's been fortified with even asbestos, things that just won't burn. It'll kind of keep the flames away. Next one is flammable liquids. Obviously, that's going to be the most common type of fire that we have in the power plant area, or just in aircraft in general. That's going to be like your fuel, your grease, your oils, paints, so on and so forth. Now, electrical equipment also very common out of all the fires. Probably the most common type of fire that you'll find on aircraft is that things short out, they get too hot, whatever the case may be. That's what ends up happening. That's a Class C fire. Now, Class D fire is metal, and believe it or not, metal will burn once it gets hot enough. So that's your magnesium, like in your transmissions, aluminum. Obviously, most planes are made out of aluminum, so on and so forth. Another one to point out here is that lithium is listed, and lithium's in a lot of batteries that you'll see. Not a whole lot of Class K fires out there because we shouldn't be cooking on aircraft for the most part, even on heavy commercial jets, they're just warming food up. They're not actually cooking. So if you see a Class K fire, something's gone kind of weird. All right, so now the power plant has several different designated fire zones. You have the engine section, the engine accessory section, except for reciprocating engines, any complete power plant compartment, so that where it's located at. Now, you also have the APU section, any fuel burning heater, so like combustion heaters and things like that on a recip engine, but also on some of these heavy commercial engines, they have fuel heaters. The compressor and accessory sections for turbine engines, which is largely going to be fires due to bleed air leaks. And then you have the combustor turbine and tailpipe section. So that obviously gets super duper hot. So it being a fire zone on and of its own itself, in and of its own accord, makes sense. Now, in addition, the engine and the nacelle zones, other areas on multi-engine aircraft, like your big heavy commercial aircraft, they are provided with fire protection and detection systems. These are like baggage compartments, lavatories, APU, combustion heater installations, other hazardous areas. Depending on the configuration and purpose of the aircraft, you can potentially have additional fire zones as well.
All right, so let's talk about fire warning systems and what different types that there are, how they work, and what that means for us as maintainers.
Okay, so a fire detection or complete fire protection system consists of two parts. One is something to detect the fire, and the next thing is something to extinguish said fire. All right, so we're going to take these piece by piece. We're going to first detection systems and then extinguishing systems, and we're going to look at them. So first off, the fire detection system. Let's just talk about fire detection systems in general. So several different types of fire detection systems are installed in aircraft to detect engine fires. Two common types are used. They're spot detectors and the continuous loop detectors. Now you should remember this both from general because we talked about them, and then we went real in depth in air. All right, so what you're looking at here is a thermal switch system. It is a type of spot detector system. Now, spot detector systems do just that. They detect fires in certain spots, and the thermal switch system is just one way that the detection system looks for fires. So these thermal switches that you see on the right hand side here, they're heat sensitive, and they complete an electrical circuit at a certain temperature. So we know that fire is going to happen at certain temperatures. All right, and we know that underneath that temperature, whatever the thermal switch is attached to is below its chemical flash point. It can't. You can get it heat. You can heat it up all the way to that point, and it won't combust or won't melt or won't do anything else like that. But beyond that, we have a fire going on, and so those thermal switches are basically there to close whenever temperature gets that high. If you need a refresher on how that works, essentially as it heats up, the resistance in a conductor drops down, and that allows the circuit to complete, and then it'll cause the light to illuminate up in the cockpit, allowing you to know that, hey, look, there is a fire on board. Okay, probably a little bit more common you'll find is a thermocouple on an engine primarily, but also other parts of the aircraft as well. These work on an entirely different principle than the thermal switch system. So a thermocouple depends on the rate of temperature rise, and it doesn't give you a warning when the engine slowly overheats. So it can just get slowly hotter and hotter and hotter, and you can watch the EGT just climb, 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 and it won't give you a fire alarm. It only throws the alarm whenever there's a sudden jump in temperature. Now, the heart of the system, I won't go into all the relays and everything else like, but the heart of the system are the actual thermocouple leads. Now they're made from a variety of metals depending on the maximum temperature which they're going to be exposed to. So there's a design decision made early on that given the temperature of the location, they decide to use certain metals. So like iron and constantan, or copper and constantan, are common CHC measurements. So like on your CHC, which is your cylinder head, temperature that they'll use there. Chromel and Alumel, another EGT one that's very common in turbine engines, which is where we're kind of focused. Now, the way that these things work is really interesting. So essentially, those two metals tied together, whenever heat's exposed to them, one of them is going to start to conduct electricity a lot easier than the other one is. Because remember, as temperature rises, resistance decreases in the system. Now, that thermocouple is going to allow electricity to flow because it's going to open up a ground. When that ground opens up, the slave relay is then going to close the sensitive relay. Once the sensitive relay closes, all the bells and whistles go off. And so that allows for physics to be in the driver's chair. If it gets hot, this is just what's going to end up happening. Like there's no other option for this. There's no computing, there's no thinking, there's no nothing. It's literally like, if it gets hot, metals expand, and as they expand, their resistance starts to drop. As their resistance drops, then the domino effect just simply happens, which makes it a very, very reliable system. Then that's why thermocouples are so popular. Okay, so another type of spot detector is going to be your optical sensor, sometimes called a flame sensor. So essentially, all that this is happening is that radiation that's emitted by fire crosses the airspace between the fire and the detector and impinges the detector front-facing window. And the window allows a broad spectrum of radiation to pass into the detector, where it impinges the face of the sensing device filter. The filter allows only radiation in a tight wave band centered around 4.3 micrometers in the IR to pass onto the radiation sensitive surface of the sensing device. The radiation striking the sensing device minutely raises the temperature, causing small thermoelectric voltages to be generated. These voltages are fed to an amplifier whose output is connected with the various analytical electronic processing circuits. The processing electronics is tailored exactly to the same time signature of all the known hydrocarbon flame sources and ignores false alarm sources such as incandescent lights and light bulbs and sunlight. Alarm sensitivity level is accurately controlled by the digital circuit, and a typical warning is illustrated here in front of you. Now, that's a long way to say that essentially what happens is that a fire is going to emit a certain type of light. That flame detector is going to see that type of light, and then it's going to digitally set off all the alarms and say, like, hey, look, there's a fire on board because I've detected that. Now, you'll see these on the private jet world. You'll see them in defense. You'll even see them off aircraft in the defense world, matter of fact. And so they're popular. They are said to be reliable, but generally speaking, whenever you look at the simplicity of some of the other type of systems, like your thermocouple system, or whenever we get into the fire loops, it starts to make sense why these are not as ubiquitous as some of the other systems that are out there. There's just anytime you introduce digital logic into something, you can get a lot done. So it has a lot. There's a lot of reasons why you would want digital logic introduced into a system. But the backside of that is that because you've increased complexity, you've also increased the rate of errors. And this is not a system that you really want a whole lot of errors with. So typically, you're going to see these types of things. And you can see them in power plant, like engine wells, stuff like that. But you also see them in baggage compartments or other compartments where maybe it's impractical to run a different type of spot detector system or Okay, so now let's talk about the continuous loop systems that are out there. There's the Kitty continuous loop system and the Fenwal continuous loop system. Now, they're all going to work largely similar to your thermocouple systems, whereas a thermocouple is going to detect heat, that's going to then complete an electrical circuit, which will then cause all the bells and whistles to go off. The Fenwal system it's the same concept. It just uses a cylinder iconal tube packed with thermally sensitive eutectic salts and nickel wire with a nickel wire center like you're looking at right here. The length of the sensing elements are connected in series to a control unit, and the elements may be of equal or varying length in the same or different temperature settings. The control unit, operating directly from the power source, impresses a small voltage on the sensing elements, and when an overheat condition occurs at any point along the length of the element, the resistance of the eutectic salts within the sensing element drops sharply, causing a current to flow between the outer sheath and the center conductor. And this current flow is sensed by the control unit, which produces a signal to actuate the output relay. When the fire has been extinguished or the critical temperature lowered, the Fenwal system automatically returns to standby alert, ready to detect the subsequent fire or overheat condition. The Fenwal system may be wired to employ a loop circuit. In this case, should an open circuit occur, the system will still signal fire or overheat, and if the multiple open circuits occur, only that section between breaks becomes inoperative. Okay, so what does that mean, and why is it important? All right, so first off, we understand that the way that this thing works is that the salts that are in between the outer sheath and the inner wire basically get hot, and as they get hot, their resistance, electrical resistance, decreases, causing the circuit to basically jump like that from the center wire to the outer wire. They all of a sudden they start to have conductivity because it's running through that eutectic salt. This completes the circuit, sets off all the bells and whistles. Now that's all fine, well, and good, but what makes it really powerful is that whenever it's in a loop, you can cut the thing in half and it'll still work. It'll still basically close an electrical circuit and set off all the fires. The other big advantage is that it automatically resets and then closes back up, it will go off, and then as the fire is extinguished, it'll reset itself. And then the same thing, if that fire crops back up again in the same spot, heats it all back up again, it'll go off again until the fire is extinguished. Now that's really, really important because let's say you're flying along and you have a compressor stall and it blows up the engine. All right. Well, as it blows up the engine, it sets off a fire in 2 or 3 different spots. Well, let's say in that explosion, it cuts the Fenwal detector in half. Well, it will still work as a detector sensing the fire elsewhere in the engine because it's set up as a loop, and so all of a sudden, like, you can lose half of the fin wall detector, and it'll still go off. Then let's say that they pull the fire bottles, puts everything out, and they think, "Woo, we avoided the fire. Let's try to find a place to land." And then all of a sudden, the fire comes back in. It lets the pilot know, "Hey, look, that fire's back on again." In the same place. And so it's actually a really it's very simple. There's not a lot of complexity to it. It's been around for a while, and so there's a certain amount of beauty to the system just because it is so simple, and it's so reliable, and it is totally anti-fragile. You can do all kinds of stuff to it, and it'll still work, and may potentially even work better. And so that is a fin wall system. So you'll see these all over aviation. Okay, so this is a Kitty continuous loop fire detection system. It's the kind of the other side of the continuous loop systems. Now, this is a continuous thermal sensing design for aircraft fire and overheat detection, primarily used in transport aircraft, so like big, heavy commercial aircraft. It protects areas like engine nacelles, power plants, wheel wells, the kind of places that you'll find Kitty systems. It provides superior coverage compared to the spot type detectors, and it's rugged enough for harsh environments like modern turbofan engines. I mean, it can get really cold, it can get really hot, it can get dirty, whatever. It'll survive. Now, the key components that make it work is a sensing element made of two wires. You'll see those two wires that kind of run the length of it, and that's how you know that you have a Kitty system in front of you. And it's embedded in a thermistor core material with an Inconel tube. That's the what you see on the outside is those Inconel tubes. They're encased in perforated stainless steel shroud for protection, and also features a control unit that monitors resistance changes, support tubes for mounting, and electrical connectors with ceramic insulation. So basically, you're going to have these two wires that are going to run around into a control unit. The control unit is basically watching the resistance of those two wires to see how they change and determine if there's a fire on board or not. So how does it work? All right, so the thermistor's core resistance decreases as the temperature rises due to fire or overheat. The control unit applies 28 volts DC and detects a change. Reaching an overheat set point triggers delayed warning, so it's going to heat up and say, like, hey, look, we're overheating, and we're going to give it 10 seconds to see if it's just a flash or if this is a sustained fire. While a further drop in the fire set point activates an immediate fire alarm system. So it can get hot and then set it off, or it can get to a certain level of heat, and then it's going to just immediately set it off because they know there's a problem. The system resets automatically when the conditions normalize and can distinguish shorts from actual fires based on the resistance of fire change. Now, all right, so the dual loop configuration, just like the fin wall system, it works the same here. So it can be just as robust. In some aircraft, it supplies the nacelle temperature data, so like it'll give you systems into AIMS, which is the aircraft in-flight monitoring system, and it lets you know, hey, look, in the nacelle, this is the temperature that's going out there, which has its advantages. It becomes like another data point, for decision making. It integrates temperatures along the entire length of the system, and provides average readings rather than just local hotspots. Now, the best advantage is that it offers complete coverage over the fire zones. It resists damage to vibration. It's really robust and will resist oil, water, extreme temperatures. Doesn't weigh anything. It gives you pretty accurate results pretty quickly, and it's really good for a fault indication for shorts. And it doesn't rely on rate of heat rise like the fin wall system does. It's simply just is pretty simple, pretty robust in the middle of it all. It can be a little testy to maintain. They are sometimes prone to false indications of fires, so you have to kind of keep that in mind. But yeah, so that is the Kitty continuous fire loop system.
Now that we understand the detection systems, what sort of maintenance can we expect to be doing on them?
All right, so the most common maintenance task that will be associated with the fire detection system is simply testing it on pre-flight. There's a test circuit that you'll get up on there if you're the one doing the avionics pre-flight. You'll go through there, and hit a test button, and you'll see all the lights come on. Nowadays, they'll have on the MFDs a fire detection system test that you'll run. It may, depending on the type of aircraft, it may actually print out a test pass, or it'll just give it an indication on the screen, and then you'll just sign it off in the logbook. But that is by far the most common task that you'll be asked to do when it comes to fire detection systems. Okay, so another pretty typical maintenance task you'll do is every so often you'll have to do an installation test on the fire loop system. Now, what this is going to look like is that you're just going to simply test what the installation or what the resistance is between the either the two wires or the outer shell and the wire, depending on if it's a Fenwell or a Kitty. And that will look like this. You'll simply pull a connector off. You'll hook up a megometer to it, and you'll run it. And the maintenance manual will tell you that it has to be above so many ohms of resistance. The reason you do this is that over time the resistance will break down, and you'll end up having to replace the loop. Now, those loops are set up so that way the time that it's time to overhaul them and fix them, it will correspond with the engine overhaul schedule. However, there are certain circumstances that could cause them to get damaged, could cause them to wear out early. If you're operating in Yellowknife and it's super duper cold, or there's been a lot of Skydrol leaked onto it, or any number of things could potentially cause a problem. Anyways, but that's really all there is to it. To these systems, they're pretty straightforward, pretty easy to maintain.
All right, now that we've detected the fire, let's talk about how do we extinguish the fire. What fire extinguishing systems exist on heavy commercial aircraft?
Okay, so certified aircraft that are operated under 14 CFR Part 23, so commuter aircraft, are required to have at a minimum a one-shot fire extinguishing system. Now, these can be positioned in multiple different places on the aircraft, include APUs, fuel burning heaters, and obviously the engine, because that's where most of your fires are actually going to happen. It's places that generate a lot of heat like that. Now, the typically this is going to have what we'll call a fire bottle, or a discharge bottle. You'll hear them kind of referred to a little bit differently depending on the aircraft and the context in which you're working, but they're all basically the same thing. They're going to be like this pack of fire extinguishing agents that are super pressurized, and you flip a switch and it discharges all of that agent into the engine or onto the engine, depending on where it's at. Now, this could be a bunch of different types of types of fire extinguishing agents. Halon 1301 is one of them, but there are other ones that are out there as well. Some of them are very corrosive, and so like if you discharge the fire bottle, you're basically canning the engine no matter what. You're just basically, the bottle is there to keep you from dying in a fiery crash. But once you pull that fire bottle, the path to getting that engine back serviceable again is pretty severe. And other ones just use CO2, and so it's very effective because it'll help displace the oxygen, and it's not corrosive. However, it's not nearly as effective as halon. So there's a trade-off there, and you'll see both of them used in different contexts. All right, here's an example of a fire bottle. It's like you can see, it's just like a little circular orb that basically gets pressurized with whatever agent is going to be putting out that fire. And you'll see these in different places throughout the aircraft, most notably in the APU. On the two engines, you may have one somewhere else, depending on the aircraft that you're working on. Okay, so now if you think about the way that these bottles have to discharge, they need to do it very quick and very effectively. And the best way to do that is just open a valve as fast as you possibly can. Well, in order to do that, to open that, to create that opening, to allow all that stuff to rush out as quickly as possible without the time of going through a bunch of, this relay has to connect with that, and then this motor has to open and or turn to open the valve, and all this other good drama. They have created what we call a squib, which is an explosive cartridge that mounts to the fire bottle. And whenever that squib has an electrical circuit that's tied to it, whenever it goes to ground, it simply just the charge in it explodes. Now, when it explodes, it blows out what's called a discharge disc. Now, that discharge disc is what's holding back all of that fire suppression agent that's inside of the bottle. Now, that fire suppression agent, now that it's not being held back anymore, will immediately try to leave that bottle, and it goes through the discharge valve, which is on the left-hand side here. You notice that it all of a sudden opens up and allows that agent to start to expand. As it expands, it spreads out. As it spreads out, it hits the fire and removes all the elements that fire needs to keep on going. And so you get that one shot of halon or CO2 or whatever the agent is directly onto the fire, and it puts it out. Now, part of the fire extinguishing system will also be to close off all the fuel to the engine, which then helps not only remove the potential agent that could potentially be on fire, because it's fuel, and it's very likely that it's at the very least contributing, if not the primary thing that's on fire. But it also turns around and keeps the engine from running, which in theory will also kill electric power. It potentially could remove any hydraulic power if the hydraulic pump is the one that caught on fire or something like that, and it basically stops the situation from progressively getting worse due to that. So as maintainers, it's something to remember. If they've pulled the fire handle, it's very likely that all the fuel valves are closed, so that way the plane can compartmentalize the fuel and keep the fire from spreading. And this can happen. People can do it on accident, and you might even swap out the engine. Then you can't get the thing to run. You're wondering why. It's like, oh, you forgot to go back and check all the fuel valves and open them up. Speaking from experience, but that is how the bottle works and how it discharges. And there's not really that much more to it. This is kind of like your one shot wonder to put that fire out.
Now that we understand the fire suppression systems, what sort of maintenance can we expect to have to do them, and what kind of concerns do we have about working on them?
Okay, so the most common maintenance task associated with fire bottles is just going to be simply inspecting the pressure. You'll do this every so often. You'll go up there and just simply look at the pressure gauge that's on the outside and make sure that the needle is in the green arc. Is really kind of all there is to it. Now, sometimes you may have to do a little interpolation based depending on the type of aircraft, or if it's reading low but you're in some kind of bizarre scenario where you've flown up into the Arctic or whatever, and all the fire bottles are low. It doesn't mean that they're bad. It just means that the temperature has dropped down, and if you're going to go right back into a warmer climate, the temperature will come back up, the pressure will come back up. Same thing if it was if you're in Riyadh, Saudi Arabia, the pressure could be super duper high because of the temperature being super high. So there's this band that you'll want to make sure that bottle stays in. Now, the maintenance manual will have all of this in there. It literally is, in terms of task, it's very simple of look at the bottle. Is it in the green arc? If it is, it's good. If it's not, then it's bad. Barring random conditions, which will also be laid out in the maintenance manual. So really, if you just follow the maintenance manual, you'll be just fine. Now, the only other thing that you could potentially be asked to do is simply look at the disc, which is there'll be a little red disc that'll be on the bottle or on the side of the aircraft, depending on the type of aircraft that we're talking about here. And if that disc is gone or damaged or whatever, it means the fire bottle has been pulled, and that's it's time for the fire bottle to be replaced and all the follow-on inspections to happen with it. But really, when it boils right down to it, there's not a lot of maintenance that happens with these things. The main thing is don't accidentally blow a fire bottle. That's the main maintenance task. Looking at the gauge and all the other stuff is easy. The main thing is respect those fire bottles whenever they're on board that airplane, and don't accidentally pull a fire handle or do anything, especially if you're doing some sort of troubleshooting that requires you to mess around with the fire system. Once that bottle goes, there is a sea of work and money that comes behind it. So you want to be very, very careful with playing around with them.